Hi, my name is Arnav Sharma. I'm going to start off by talking about motivation and context. Research question: how do changes specific variables such as height, material of the ball, and type of surface affect the inelasticity of a collision? So the main outcome we discovered is that as the drop height increased, the ball's speed and kinetic energy at impact also increased. Because of this greater impact energy, the ball lost a larger fraction of kinetic energy in the collision, and making the collision more inelastic. So our motivation for this, so we want to understand different factors such as height, material, object, and type of surface affect the elasticity of the collision. The reason why we wanted to research this topic is because we're interested in conservation of energy and how different factors affect it. So our goal was to figure out how the changes in height when dropping the ball affects the elasticity of the collision. So some background info. So in an elastic collision, kinetic energy is not conserved because some of it is transformed to other forms of energy such as heat, sound, deformation. However, the total energy system stays the same, but the kinetic energy of the motion decreases. So the type of material really affects how elastic or inelastic collision is. Hard materials tend to bounce back with energy loss, while softer or more flexible materials lose more energy and more inelastic. Friction between surfaces also plays a role. Smoother surfaces reduce energy loss, while rough surfaces increase it. Kinetic energy is not conserved when the ball collides with a soft surface as compared to a hard surface.
So for our experimental design, our independent variables were the height which we dropped the ball. Our variables we kept constant were the ball, the type of measurement we used, the surface we were dropping the ball on. We used a meter stick to measure the height of where we dropped the ball, a camera to film, and Tracker to collect our data. Tracker was the best tool for this project because it allowed us to track the movements of the ball when dropping it. This addresses the problem by dropping the ball at different heights, recording the data on Tracker, and keeping all other factors consistent. We are able to clearly identify how inelasticity of a collision is impacted by height. Minimizing inconsistencies. In order to minimize inconsistencies, we had ensured that we were using the same ball for each trial, dropping the ball exactly at the correct height, and when we dropped the ball on the same surface to help reduce any confounding variables that might be present. We calculated the uncertainty of the experiment using the formula on the data analysis slide, and then that's just like what we were doing in that picture.
For models and representations, we decided to use the models of conservation of energy, which is the idea that energy is being converted throughout the entire system. To represent this, we tried using pie charts and motion maps. So the energy pie charts show how energy is being converted and conserved and converted throughout the entire experiment. So the motion map showed the position, acceleration, and the velocity versus time of the balls as they change in energy. The longer arrows first show the ball as it falls downward and its acceleration. The first set of short arrows show the ball after it bounces on the ground and the change in energy that is depicted. And then the second set of short arrows show the ball slowing down and less potential energy that is there after each bounce. We also drew a system schema, which was our rubber ball and our flat ground were included in this scenario. We had the force of gravity pulling down on the ball, and then we had the elasticity of the ball. The two equations we used are in the top right corner, which were the conservation of energy and the kinetic energy being transformed into different types of energy. The first one was kinetic energy 1 plus potential energy 1 is equal to kinetic energy 2 plus potential energy 2. And then our next equation was half mass 1 plus times the velocity 1 squared is equal to half of the mass 2 times the velocity of the final squared.
As for the data analysis, we accounted for error by minimizing it by doing the following: making sure that we dropped the ball at the exact same mark, being consistent with the reference frame when tracking data, ensuring the camera was held at constant position and laying on a flat surface level, making sure the ruler was held straight, allowing the ball to hit the ground and bounce up at least once in a trial. And when analyzing data, we used a consistent reference axis across all trials and tracking at least 50 data points for each trial. And to determine the inelastic equation, we used the equation sigma 1/2 m initial velocity squared is not equal to sigma 1/2 mass times final velocity squared. The mass of the ball we measured at 0.09305 kilograms using scale and class. And for the initial velocity and final velocity, we found that using Tracker. And then we also chose to quantify the velocity using the equation I, which stands for inelasticity, 1 minus kf over ki. So we did that for every single trial. So we dropped the height at 1 meter, 0.6 meters, and 0.2 meters. And then to estimate uncertainty, we used the equation delta x equals the square root of delta a over a squared plus delta b over b squared. And our data shown on the slides.
This is just the answers for all of our series that we calculated. And then these are our graphs from Tracker.
So for our scientific reasoning, our data supports the idea that when the ball is dropped from a higher height, it has a greater kinetic energy and hits the ground with a larger speed. With a bigger hit, the collision is more inelastic, so more of the energy is lost and there's a smaller rebound. The lost energy does not disappear, it goes into sound, a bit of heat, and deformation of the ball on the floor. At a lower height, the ball is has less inelastic kinetic energy, so the collision is closer to elastic and the rebound is larger relative to the drop. We kept the error small by trying to drop the ball from the same mark, keeping the camera at the same height and steady, the ruler straight, and we also used the same flat surface consistently between trials. We also tried tracking as many reference points in the same frame, and any differences we saw were likely from timing limits of the camera, the parallax, or setting up and shifts, or small setups in the shift. Overall, results match our expectations. The higher the drop leads to a bigger loss of energy and more inelastic bounce. So we did not see any discrepancies between our models and observations, at least to our knowledge. Any source of error may have been just from not dropping the ball at the exact mark at every trial and not holding the ruler completely straight and calculations within our work.
Our initial prediction was the total kinetic energy will be higher when the height of the ball being dropped is higher. We were correct in our predictions. When we dropped the ball at higher heights, the kinetic energy was higher. This is because the energy is conserved in our closed system. When dropping the ball at higher heights, that energy then converts to motion, which in turn gives us a higher speed. The higher speed then gives us a higher kinetic energy. For future experiments, we can make sure we keep all our variables as consistent as possible. One example of this is keeping the ruler straight.